Welcome to Spring LIB.
In this exercise, we're going to be talking about radius of curvature and circular motion. So before we dive into the exercise, I'm going to briefly review these concepts. First, if we have a certain curve that I'm drawing here, an arbitrary curve, and we want to know the radius of curvature of the curve at a certain point that I'm calling x0. Okay, so we have y as a function of x, and we want to know the radius of curvature at this point. The formula that we must use is that the radius of curvature is equal to 1 plus the derivative of y with respect to x squared to the 3 halves divided by the absolute value of d2y dx2. And this all must be calculated at x0. Okay, so this is the radius of curvature. And about circular motion, what we need to know is that when we have a body that is undergoing circular motion, we can decompose the particle's acceleration into two components. So we have one component that is centripetal, that points towards the center of curvature, and another component that is tangential. Now, this centripetal acceleration is equal to v squared over r. R is the radius of the circle, and v is the speed. And it accounts for the change in direction of the velocity, while the tangential acceleration accounts for the change in speed and is equal to the derivative of v with respect to t. So now we can dive into the exercise. So we have a car that has a mass of 2 megagrams and makes a trajectory that's shown here in the picture. Y is equal to 20 times 1 minus x squared divided by 10,000. And our goal is to find what is the maximum velocity of the car when it is at the crest of the curve. So at this point here, we want to know what is the maximum velocity so that the car does not leave the surface of the road. Okay, so how do we proceed? What I'm going to do first is to find the radius of curvature, r, and then with the radius of curvature, I'm going to apply Newton's second law in order to find what is the maximum velocity. So let's proceed. So first, in order to find the radius of curvature, we need the derivative of y with respect to x. Now remember that y is equal to 20 times 1 minus x squared divided by 10,000. So dy dx is equal to minus 2 times 20, so that's minus 40 times x divided by 10,000. So this is equal to minus x divided by 250. We also need the second derivative, and that we obtain just by differentiating the first derivative, so it's minus 1 over 250. So this means that the radius of curvature, notice that the first derivative, if we apply it at x equals 0, that's the point we're interested in. This is equal to 0. So the radius of curvature is 1 divided by the magnitude of the second derivative. That's just 1 over 250. So r is equal to 250 meters. So this is the radius of curvature. Now we can calculate the maximum acceleration. So what I'm going to do is to draw the free body diagram on the car. So this is the car. The forces that act on the car are the normal, acting upwards, and the gravitational force acting downwards. And notice that the total acceleration of the car is pointing downwards. Okay, assuming that the car has constant speed and is undergoing a circular motion at the crest. So at this point here, we can consider the motion to be a circular motion with a radius of 250 meters. So this means that mg minus n is equal to, according to Newton's second law, the mass times the acceleration. So that's m times v squared over r. Now, in order for the car to have contact with the road, n has to be greater than 0. So at the limit, we can consider the situation when n is equal to 0. In that situation, when the car is about to leave the road, we have mg equals mv squared over r, meaning that v squared is equal to gr, or v is equal to the square root of gr. Now g is 9.8 meters per second squared, while r is 250 meters. So the value of v is equal to 49.5 meters per second. So this is the maximum value of the speed of the car when it's about to leave the road.